Alright, so I think this is recording. Let's take a look at some more factoring examples to see if this can help some people. I have these worked out and hard copy posted on the school website. If you look under the weekly folder, there are a file to open up that has the solution to the 18 examples. I've gone through and made videos that explained examples 1 through 6 and then explained examples 7 through 10. And now let's see if we can, in this video, finish the rest of these problems. Alright. So here let's take a look at example 11. Now, I didn't cut and paste my work like I did in the previous videos. I'll just write it out, but I'm not sure if writing it out helps a little bit more or seeing it typed up where you can read I don't know if you can read my handwriting or not. When I have 4 terms, I cannot apply our X method, our way of factoring. That X method needs to have be a trinomial and have the degree of the middle term be half of the degree of the leading term. We can, however, factor this by grouping. So we're going to group the first 2 terms together, x to the 6th minus 2x to the 4th. And we're going to group the last 2 terms together, the minus 16x squared plus 32. Now you'll notice that I put the parentheses around the last 2 terms. I didn't put it, if I would have put it here around this, that minus sign then would have been applied and made that 32 a negative. So I'm basically rewriting subtraction as addition of the opposite. So you can think of it as that I'm changing the original problem to be plus a negative 16x squared. That way I don't make any kind of silly sign error. So I focus my attention on these first 2 terms and say, what do they have in common? Well, they don't have the coefficients anything in common, but this term has 4 factors of x and this one does as well. So I can factor out an x to the 4th. Inside the parentheses, I still have a binomial. I still have the subtraction. If 4 of these factors are now gone from the first term, I have 2 factors remaining. And if I took this factor of x to the 4th out, I have that factor of 2 there remaining. So what I'm hoping to do in this factor by grouping is I'm hoping to see this factor appear over here in this term that'll be common to both. So it gives me a little bit of an idea of what I'm going to factor out. So if I want this to be a 1x squared, I need to factor out a negative 16. And if the negative times a negative will be positive, and 16 times 2 is 32. And hey, now I have terms are separated by addition or subtraction. So with respect to this subtraction sign, this first term has 2 factors here. The second term has 2 factors. What's common to both, here in this first term, I see x squared minus 2. Here in this, I see x squared minus 2. That is a common factor to both terms. So if I factor the common factor, if I pull out the x squared minus 2, inside the parentheses I'm still going to have this subtraction, and now this factor, this has been factored out, leaving me with a factor of x to the 4th. And this x squared minus 2 now has been factored out, leaving me with 16. So I have to be careful I'm not finished with this yet, because I can't do anything else with this x squared minus 2, but I definitely can continue factoring this because this x to the 4th is a perfect square. If you have x squared squared, if you have a power to a power, you multiply the exponents, and 2 times 2 is 4, minus, and I can rewrite 16 as 4 squared. So I have a difference of perfect squares. We've seen before that we can factor that to this base, which is x squared, plus this base, which is 4, times, come back to that base, minus this base. All right, well, I can't factor a sum of squares, but I can factor a difference of squares. See, I can keep going. The x squared minus 4, it factors because I can rewrite the number 4 as 2 squared. So I have a difference of perfect squares. X is being squared, 2 is being squared. The difference means I'm subtracting them. So I have my previous work, x squared minus 2, x squared plus 4. And now I can factor this to x plus 2. Those are the two bases, and I can add them, and then I'll subtract the two bases, the x and 2. Now, if you've done this problem or a similar problem, you could shuffle the order of this multiplication. You know, the order of the multiplication is not important. I could have the x plus 2 times x minus 2 first over here. Now, if we had any of these factors that were repeated, you know, if we have an x times x, we're going to express it as x squared. But see, I don't have another x squared minus 2. I don't have another x squared plus 4. So this is my final answer for problem number 11, and that's probably one that's a similar problem on your weekly. All right, so let's take a look here at number 12. Now, this time I'm not going to factor by grouping. I have 3 terms. The middle term has a degree of 2, and that's half of this first term has a degree of 4. So the middle term has a degree that's half of the first term. So I'm going to use my x method here. But remember, when you're trying to factor an expression, the first thing that you really want to look for is their greatest common factor. It's going to make our arithmetic easier, and in some cases, sometimes your techniques only work if there's no common factor among the terms. So I can see here pretty easily, and if you can't see it easily, you can grab a calculator, that all of these numbers are divisible by 6. So I can rewrite this as 6 times x to the 4th plus 6x squared plus 8. Okay, so now I can apply your x method. And normally when I'm showing students, I write the x over to the side, but I mean, some of you like to just put it directly over, and there's I don't have a problem doing that. I just often write it over to the side so that this doesn't get so cluttered that I can't read it very well. But here with this, I can write big and I can write in different colors, so it's going to be easier for me to see it, so I don't have a problem putting the x directly over that middle term. So now for the 6, it temporarily stays where it's at. I'm going to ignore it for a minute. And this leading coefficient 1 here, I'm going to take the first term times the last term. I'll get the value that goes to the top of my x. And now the game begins to try and search for two numbers that when multiplied together give me this expression on the top of the x, but yet when added give me on the bottom. Well, it doesn't take you very long to see, hopefully, that, that 2x squared times 4x squared is 8x to the 4th. Because when you multiply with the same base, you add the exponents. 2 times 4 is 8, but 2 plus 4 is 6. So hey, we have found it. Now, when the leading coefficient is 1, you won't have to come over and make your table and stuff. We can easily come in here and say, okay, x squared times x squared is the only way to get x to the 4th. And we have a plus 2 here, and we have a plus 4 there, because those were the values that the coefficients that we found in our x. We can't factor a sum of squares, you know, like the x squared plus 4 doesn't factor. Had that been x squared minus 4, we could have kept going. So this is our final answer, and don't forget that you will need, if you factor out a common factor, sometimes people will have that work up here. They do some other work, scratch work over here. You have to remember to include that 6 in your final answer. All right. Now, if I forget the formula for the difference of squares, I've showed you in a previous video, and if you look at the very first example, I think it was x squared minus 9. I show you that hey, you can use the x method. You can rewrite x squared minus 9 as x squared plus 0x minus 9. And you can do your x method, and you'll be able to factor this to x plus 3 times x minus 3. There's not really a nice way for us to derive this x cubed plus 64. As you gain experience and begin to learn about zeros of polynomial functions, you can derive this a little bit easier. There is a website, the address here, Math Central. I just simply Googled derivation of the sum of cubes, and you can read this because you can pause the video and get the web address, and you can see that the person is arguing that a minus b is 0, that if a equals b, then you know that a minus b is a factor of this, and so through long division, if it's a factor, your remainder is going to be 0. They find that quotient, and they realize, hey, this can show students how to know this formula through long division and not through memorization. But sometimes, long division isn't always the easiest thing in itself to fall back on. Then I scroll down below here, and they're looking at it through a geometric representation. And first they're using numbers and stuff, so you can see here that they've got a cube, that they have a base here, along here 4 places, along there 4, and a height of 4. So a 4 by 4 by 4. And they're cutting out this 2 by 2 by 2 up in the corner, and they're showing you down here how that cutout can be expressed in groupings. And through a little bit of time and effort and studying these and understanding how that pattern works with numbers, and then they do it for a larger cube, then they can say you can generalize that, and by generalization you can derive this formula that they gave us up here. But for most of us, we're just simply going to have to rely on the fact that we have a formula memorized, that if you have a cubed plus b cubed, that's equal to, well, this first one is 2 terms. It's a binomial. You keep the same sign. Over here, both of these are only going to have one negative sign, and the expression here and the expression here are always opposite in sign. So these guys are always opposite in sign, and this are always the same in sign. So that's how I remember, because if they change this on me in the next example, it'll probably be a subtraction if I remember right, and the formula will be a cubed minus b cubed is equal to, well, I'll keep the same sign. Since that's minus, this will be minus. Then I take that base and square it. I multiply the 2 bases together. I know that this term and that term, that the signs there are opposite, plus the b squared. See, there's only one minus sign that appears in my formula, and it changes location, but here this sign is always the same, and this term, this sign and this sign are opposites. That's one way that you might be able to memorize that formula. However you memorize it, whatever trick that you use, if you have a song that you sing or hum to yourself, hey, you use whatever works to help you to memorize this. So we can rewrite this x cubed plus 64 as x cubed plus 4 cubed, and then by just substitution we'll keep the same sign. Since that's positive, it'll be x plus 4, and over here it'll be x squared minus. Now my formulas tell me x times 4, but that's the same thing as 4 times x, and we usually write the coefficients first. We usually don't write it as x times 4. We express it as 4x. There's nothing wrong with it, I guess, if you did that way, but it's not what they call standard form. You're not going to see it that often. And then here, I take that base and square it. So 4 squared, which we're going to write 4 squared as 16, right? 4 times 4. So just by knowing that those formulas that I had written there previously, just through a direct substitution, we can factor this. If you forget the formula, well, then you're kind of out of luck, because I don't think this is necessarily the easiest thing to derive. Once you gain a little bit more experience, like I say, and understand that when you have something that's a factor, then when you do division, you have a zero remainder, then you might be able to do this in long division. And that's what maybe taking the time and effort to look at. So you've got to fill in the zeros that make the long division line up. Take some time to look at that if you're an advanced math, if you truly want to understand it in depth. So here on the next example, right, I was anticipating that instead of x cubed plus 64, that it was x cubed minus 64. We recognize 64 is a perfect cube because 4 times 4 times 4 is 64. So I know that I can rewrite this as x cubed minus 4 cubed, and then through just a substitution of knowing my formula, I'll have the two bases that I subtract, and then I have squared plus I multiply the two bases together, and then I square this guy. So you can see how similar the answers are, and you can see how easy it is to get the formulas backwards. So take some time to memorize it, and hopefully that won't happen to you. All right, now here we're back to just a pretty basic problem that we can apply your X method. If when the leading coefficient's 1 or the leading coefficient's prime, the X method really isn't all that much of an advantage. Its true advantage comes when this leading coefficient is larger than 1, and especially when it's not a prime number, when it's a composite number, because it helps us to factor it in some organized way. But sometimes people just like to simply keep in practice, and they like to do it. With the minus signs, I'm always fearful that when somebody draws their X, they'll draw it through there and accidentally change that minus sign to a plus sign. So I do caution you on that. So if I place my X over my middle term, multiply the first term times the last term, I get negative 20x squared. Two numbers that multiply together to give me negative 20, but add together to give me a negative 1 are negative 5x and positive 4x. And I don't have to come over and use a table and factor both horizontally and vertically, because since the leading coefficient is 1, I know that this is x, and that this guy is going to be a minus 5 and a plus 4. Or the order doesn't matter. You could write plus 4 and minus 5. But that's our final answer. That's typically how we have. If you forget, if you do come over and draw your table, and put the first term and the last term and the entries from your X in there, you're going to see, if you look at this horizontally across here, that you have a negative 5 that's common to both factors. If you look here, you see that a 4 is common to both factors. If you look across on that top row, an X is. If you look across in this first column vertically, an X is common. An X is common. And so you see we have X minus 5 and X plus 4, which is exactly what we got before. So like I say, this table doesn't have its true advantage when the leading coefficient is 1, because you can really just look in there and say, hey, I'm looking for two numbers that multiply together to give me negative 20 and add together to give me negative 5, and then just write the numbers there. But when this leading coefficient is not prime number, and especially when it is a composite number that has a lot of factors, a number like 12 or 24 or 36 might have a lot of, it might take some time and effort to go through this trial and error to find these values in your X, and then to make your table. All right, so let's move on. So, well, here's kind of a similar situation to that. We've got a trinomial. We can apply our X method, and our first step always in looking at this is to look for the greatest common factor. It looks to me like 5 is the greatest common factor, or 5 is at least a common factor. Now, sometimes I'll accidentally do a problem and I'll find a common factor, and then later I'll recognize, well, I didn't factor out the greatest common factor, but 5 is. That's and sometimes you'll have a 5, and then later you'll look at it and go, oh, wait a minute, I could have factored out a 25, or I could have factored out a 35, or whatever, some larger factor, because we want to find not just a common factor, but the greatest common factor will help us to reduce this problem and make it easier for us. So if I factor out a 5, what do I have? Well, the 35 divided by 5, I'll have 7x squared. If I divide the 285 by 5, the calculator tells me, I believe it, that it's 57. And the 280 divided by 5, that's a little bit easier. I see that that's 56. All right, so here's a perfect situation where the x method might be, helpful and stuff. At least 7 is a prime number. It's not going to be real difficult, because if 7 would have been a large composite number, it would have made the problem a little more difficult. Let's place an x over our middle term. We'll take the first term times the last term. If we take 7x squared times 56, my calculator's telling me 392. So hopefully I'm not making any keystroke errors, if I accidentally punch in the wrong numbers, but that looks right. So now I need to play around with factors of 392. Maybe over here I'll come over and say 392 has a prime factorization of 2 times 2 times 2, which is 8, times 49, which is 7 times 7, and then I'll try to group these together in such a way. Well, it looks to me like if I group the 2's together, that'll be an 8, and if I group the 7's there together, that'll be 49, and 8 plus 49 gives me my 57, and I know that 8 times 49 is going to give me. So I've just stumbled upon it just looking at the prime factorization pretty quickly. Sometimes that may take you a little bit of time and effort playing around with these factors. Maybe the first time you looked at it, you grouped the 2 times 2 together, you had 4 times the 98, and you realize, well, that's not it, because it's already bigger. One of the factors is already bigger than 57. It might take a little bit of time and effort to group those together, right? But to save you some time, I would suggest looking at the prime factorization, or just simply learn how to play around on your calculator pretty quickly, and you can do it. All right, so if we make a table, and remember, I'm leaving the 5 alone. I'm only working inside the parentheses here. If I write the first and the last term along one diagonal, and then the numbers that we found in our x, they're going to go along the other diagonal. Here's how we're using them. So I look horizontally and I say, well, does 8 and 56 have a common factor? Well, yeah, 8 divides 8. 8 also divides 56. And so I write, yeah. You can't see it, but my pen is getting wrapped up around my cord there, and I can't write. 8 is common to both. If I look here, I see an x common to both, and both are divisible by 7, so I've got a 7x. If I look vertically, 7 and 8 don't have anything in common, but they do have a variable x that's in common. And if I look here, this one is missing an x, but they're both divisible by 7. So, I'll check real quick to make sure I haven't made a silly mistake. 8 times 7 is 56. 8 times x is 8x. 7x times 7 is 49x. And 7x times x is 7x squared. So it looks like that we factored this correctly. We've got x plus 7 and 7x plus 8, and we're done. Now, for the pre-AP people on their weekly and stuff, I accidentally gave 3 of the problems equations equal to 0, and I meant for all of them to just be expressions. We factor expressions, and when it's equal to 0 to solve, if we solve an equation, then we set that equal to 0 and find the individual solutions. But for right now, my intent was to just simply practice factoring expressions. One of the reasons that you practice to factor is so that you can use it as a technique to solve equations. Alright, so I think I have 2 more and then we'll be done with this video. I'm not paying attention to the time, but hopefully it's not too long. We've got 4 terms. We can't apply the X method. We do have this in descending order, 3, 2, 1 in the constant term. I'm going to group the first 2 terms together. I don't have a minus sign like last time, so I'm not fearful of my grouping. If I look to the first 2 terms, numerically they're relatively prime. 4 and 5 don't have a common factors, but both of these terms have an x squared that's common. So I'm hoping that this 4x minus 5 is a factor, since it's in this first term, that it appears over in my second term. So 12 and 15 do have a common factor of 3. If I factor that 3 out, then look here. 3 times 4, I've got 4x. That's minus, that's positive, so I need this to be minus. 3 times 5, hey, 15. So I have 4x minus 5 as a factor in this first term, 4x minus 5 that's a factor in the second term. If I pull out that factor, I'm still going to have this plus sign that appears here. This factor is no longer there. It was pulled out. I have x squared. This factor is no longer there. It was pulled. See, to be a common factor, it has to appear in both places. When you pull it out, when you write it, that takes care of because of the distributive property, all the places that it would be in the inside of the parentheses. I can't factor x squared plus 3 any further. So hey, this is our final answer and we're done. So the factor by grouping is something that's not to be afraid of. You just need practice with it, but really it's pretty easy once you get used to it. But then we can say that about a lot of things. Alright, so here I'm back to a trinomial, so it's in descending order. I'm going to look to see if there's a common factor of all these and then try and apply my X method. So I think that all these numbers are divisible by 3. So if I factor out a 3, what do I have here? X to the 4th plus 2x squared minus, and if I take the 3, that's 37, 35, 35. Alright, so let's give myself a little bit of room. See, I love this thing that I can move things around or change colors, or I can do a lot of things with this wireless tablet. Alright, let's apply our x over here. Let's take the first term times the last term. And remember, I can do that x method because the degree of the first term is 4, half of 4 is 2, and that's my second term. If I had x to the 4th plus 2x minus 35, I'm not going to be able to apply this x method. This x method, I can apply it if I have 3 terms, if I write the expression in descending order, and if the degree of the middle term is half of the degree of that first term. So I've got a product of negative 35 x to the 4th, 2 numbers that when multiplied together give me the negative 35, but when added give me 2, and x squared times x squared is x to the 4th. So I have this 3 that was there. Since that leading coefficient is 1, I can come in here and say, well, x squared times x squared gives you x to the 4th. And I can just use the 7 and the minus 5. I don't have to come over and construct a table. I can just go plus 7 minus 5. Now, I do have a difference here, x squared minus 5, but I'm not going to have to worry about factoring this over the set of integers because this 5 is not a perfect square. So I'm going to leave that as my answer. Alright, so hey, that finishes up my examples for factoring. This will be up all year that you can refer back to it. Factoring is a skill that pretty much in the higher level math classes in high school, you use it all the time. So there might be a stretch where you don't use it, but then all of a sudden you come back to some skill that requires it. So it's good to kind of just have it in your back pocket and to occasionally review it, so you don't have to learn it all over again from scratch. Hope this helps, and I will talk to you later.